Hello, hello. Can you hear me? Can you hear me? Can you hear me? Can you hear me? Of course, I'm talking to myself. Um, cool. Okay, I think that works. I think we're good. OBS says it's streaming. Everything looks good. Okay. Uh, Welcome, everyone. I guess it's been a while. Please let me know if you can't see. I've increased the resolution so that hopefully everyone can see my screen without having to squint too much. Um, so this is today I want to talk about what techniques that you'll probably need to use when going on the kernel exploitation module. So this is the kernel exploitation module for CSE598. It was assigned like a week ago. These are, crazy challenges done by the evil mastermind of KyleBot. So you are having very simple kind of kernel heap. You're basically walking through what kind of like a real world kernel heap exploitation looks like. Why this stuff is important. Maybe, I don't know if we've talked about this, but KCTF is a KCTF competition. VRP maybe. Yeah. So KCTF is basically, it's actually kind of a crazy delineation, but KCTF is technically this Kubernetes CTF. That was a Kubernetes infrastructure for CTF competitions. And they have a vulnerability research program where they will give bounties for people who can pop their infrastructure. And what it boils down to, you'd think the K for Kubernetes would mean that, hey, this is all like attacks against Kubernetes and stuff. The answer is no. It basically boils down to a Linux pwning CTF. So if you find a bypass, you can report it to them. There's a whole kind of way that you can exploit these things and submit. You can do 0 days, which means previously unknown vulnerabilities, or N days, vulnerabilities that nobody that has already been public but haven't been exploited. The idea is they've like locked down this Linux kernel enough that they think that that they want to see what kind of techniques and tricks you're using to exploit this thing. And yeah, it's really cool. There's like a lot of details here. There's a Discord where they talk about it that you can join to see there. You can see all of the 1 day, like N days versus 0 days that people got it. This is all like public stuff. I guess they don't show who does it, but you can. Oh, there we go. VRP. Oh, crazy. Yeah, I don't know all the details in here, but basically, let's say, where's the KCTF? KCTF VRP bounty. Oh no. Yeah, VRP bounty. Okay. I can't remember if this is the latest one, but oh yeah, they have a similar one with V8 CTF. I guess where is the bug bounties are very large. Where is the freaking thing? Okay, I can't find it, but you can earn up to like, I don't know, 70K or something like that for exploiting this. And the interesting thing is that they're not looking for, they're looking for techniques. They actually don't care about vulnerabilities. That's why end days are in scope, but they really care about identifying exploitation techniques. Okay, so as part of this, what actually came out of this platform, or sorry, what you may or may not know, but KyleBot, who created these challenges, why isn't this centered? That's going to drive me crazy. Okay, great. Has created a bunch of techniques based on understanding the Linux kernel. And so that's what we're going to dive into today. What I want to cover is this Retsfield technique. So you, as a person in this class, or a person just, I don't know, in the wilderness online who happens to be watching this stream for whatever reason, you want to know, hey, how do I take a Linux control flow hijacking and use that in the Linux kernel to gain root privileges? This seems like a really straightforward case, it actually kind of it seems straightforward, right? Kind of when we talk about exploiting user space applications, your goal is to get a control flow hijacking, and then from there, you can ROP and do all kinds of cool stuff. Um, but it turns out that actually there's a lot of mitigations in the Linux kernel now that make that difficult and make going from getting a control flow hijacking. So what is control flow hijacking? You can control the instruction pointer and go to wherever you want. Now, we know in user space applications, when typically we can control the stack, this is actually very trivial in some case, because our payload for controlling the instruction pointer is also in line with our data on the stack, which we can use to do ROP and all that cool stuff. Now, what we realized, and part of what we explain in this paper, is that control flow hijacking on the Linux kernel now almost exclusively deals with heap vulnerabilities. Why is this? It's important to think about. Well, it's just like stack overflows in the kernel are very, very, very rare. I would assume they have some kind of static analysis or something that they're doing there. But basically, these types of what we see in user space is not really what we see in kernel space. So it's heap overflows, and the types of essentially you can think of the fields that we see in objects that are allocated on the heap. I mean, I say objects, but you can think of a struct, right? The goal with kind of all this heap shenanigans is to make it so that you can overwrite a function pointer on the heap, and now boom, you're getting control flow, and you can redirect control flow wherever you want. Of course, the problem is then, what the heck do you do with all of this newfound control flow that you are getting? And that's where retspill comes in. So there's actually a large history of techniques here. I will kind of show some of them here. This is then the beauty, if you've never read an academic paper, I encourage you to read it. I think it's pretty easy to read. And all of these little brackets with numbers will link to, you can look at them. They actually link directly to the references where you can read more information. That's one of the super cool things I think about academic papers. Kind of helps this information, and it's easy for you to deal with them here. So you used to be able to, this like ret to user, what you could do is actually jump back to user space code where you'd have your kernel shellcode there in user space. And so you would call into the kernel, you'd do some stuff, you then trigger your control flow hijacking, and then jump back to user space. But this, they introduced a mitigation. I guess that's SMAP, this pivot to user, or SMEP. But anyways, these are two techniques that basically disallow kernel from either returning directly and executing user space code, or directly accessing with read-write privileges user space code. So these techniques, SMEP and SMAP, kind of prevented the easy access of user space code from here. These required primitives, so FHP here is control flow hijacking primitive. So you have to start from that. And you can see that each of them kind of requires some additional primitives. So you need control flow hijacking plus like a code base leak, which actually a lot of things have. But this requires changing the CR4 register, requires RDI control. And there's actually a mitigation of this CR register is the thing that actually enables these security features. So by pinning that and making it so that you can't change that, that gets rid of this. So all these techniques are kind of no longer applicable in modern kernels and their deployment. Run command, so you're just calling run command directly, but you can do this, but you need to know where you are on the heap. So you need a heap leak and you need RDI leak, or sorry, you need to control RDI. Anyways, so you can see there's all these techniques. What our technique does, and what we're going to look at, is how can we do this and execute arbitrary, not just call arbitrary functions, but also arbitrarily read and write to memory, and how to do all of this in kernel space. In kernel space with just a control flow hijacking primitive, and knowing the code base, so leaking the layout of the Linux kernel itself. Assuming we know that, then we can actually do all of this, and we can do it reliably. We can actually do our payload multiple times, which is kind of cool. and it is fairly resistant to a lot of modern mitigations. Cool. Okay, so enough talking. Let's get into some showing. So this is the kernel module. I've actually here, I guess we'll pull up the desktop. So I've created a vulnerable kernel module. We can look at it really quickly. It's incredibly simple. There's like nothing, absolutely nothing fancy here. But, oh, that's weird. Okay, don't like that. Let's open up good old IDA. This is the one. It's the same, but it doesn't matter. I've just made this kernel module. Yes, debug. Great. Don't care about that. Okay. And cool. So we have device open, which should be very simple. Return 0. Device release, do nothing. The init module that we can see does a proc create. So it's creating a proc pwn.college. This fops, this file operations. We can see that this struct we have ioctl and release. Oh no, did I not do open in there? Will this actually work? Let's see. So the device ioctl, very simple. If command is not equal to 1337 int, although I really should change this to hex because it bugs me that that's not hex. Do that, then call arg file. So yeah, so this arg is a function, is considered as a function pointer. It's basically control flow redirection. So we can see here that, where is that? Oh, I see. It has to call into this x86 indirect thunk RDX, but is calling into there. As long as it's -1, it will call whatever we pass in as the argument there. So this should allow us to redirect control flow. Okay, so we have all that. Boop, boop, boop. Great terminal here. Awesome. Terminal went away. That's exactly what I wanted to have happen. Yep, okay. Of course, the thing didn't go in correctly. That's fine. All right. So, should be able to connect to this VM, assuming I started one, unless I messed it up, which let's say we did. All right. Should see it booting up. Okay, great. I'm running this in practice mode. That's why I can load my own kernel module. In case you were wondering. Okay, VM connect. Now I'm in the VM. Okay, I have this proc pwn.college. Very first thing we need to do something to trigger this. So let's open up. I got some notes here, kind of, but okay, SSH, hacker. Actually, maybe you want to see this, I don't know. Hacker at pwn. This is using tramp to get the file there. Let's see, I have this demo K module. So let's say poc demo.c. Okay, and then, all right, so I know it's in proc pwn.college. I should probably just get, obviously if I was doing this a lot, I would do whatever, have my template that has been talking to proc pwn.college, which you probably already have from talking to the other modules. Holler if you can't. No, I won't make you holler. I will just increase the font size because that's what the people want. Okay, that may be too big, but okay. Int fd equals open. From college. Open 2. The O flag, I can never remember. So first, I'm gonna link this in, and then there's like, oh, I actually don't remember which one. Let's just open this for R read write. I don't remember which one is necessary for an ioctl. I actually haven't tested this. I just built this module before class, so hopefully, or before this office hours, so hopefully we'll see something. Okay, get the FD. and then ioctl. Oh, if FD is less than 0, P error, open. Just some nice things. There's always, it's one of these things like as you're doing this, you have to fight with yourself of like, do I actually need to check for error conditions because I'll just know it failed. What I've learned is if you saw it took me like, I don't know, 5 seconds to code this thing up. And now if this failed because these permissions were incorrect or something, I will know what went wrong and when, and then P error will give me better error output. So that's a good tip for when you're doing this kind of stuff. Okay, cool. ioctl. Now, one thing I have to be careful about as I'm looking at this is I'm using, I need to know that I'm running on a Linux system. So this man page that I'm looking at is actually technically the wrong man page. It's the man page for the Mac, which uses BSD under the hood. So we'll ignore that. But the function signatures are the same. So the return value. So the file descriptor, the request, that's 1337. And we know it's not hex, which is really annoying, but that's okay. That, and then, yeah, so then that's the request, and then the next one is the arg. So let's say 41, 41, 41, 41, 41. 6 of those. Now, if ret is less than 0, because that's the error condition, again, we're going to p error. Bah. Otherwise, return 0. All right, got my pack here. Okay, I'm in the VM. One thing I will definitely do, and I will show now, is, so I'm in the VM. What are VMs fundamentally? VMs are slow, if you think about it. Demo, K module, GCC, -o, POC. So if I'm going to compile this, I'm going to do it outside of the virtual machine. Switch back, and of course, if I was using my own terminal, I'd have tmux set up with all these things. Maybe I'll do that later. But then I can go back and forth between the VM, demo, K module, POC. Killed. Okay. Good, bad, who knows? Okay, something happened. We didn't see any P errors, which is interesting. Cool, sick. Okay, so running strace, we can see that we had the open at. So the open worked. We opened pwn.college with O read write. It returned us 3, which is a new file descriptor. Great. Called the ioctl, and then we got sig killed. Just boom, straight killed, straight to the process. I don't know. Then great. So let's debug this. See what's happening. Okay, and I'm in the VM, so let's go here. Nope. Let's go here. And let's see. Okay, so reading all these symbols. Ooh, I need to put the breakpoint, not you, person, but on this debug. Device underscore ioctl. I wonder if that will work. Nope, that definitely won't work because it's not defined. Okay, great. Now the question is, I haven't done this enough to know, does this kill the thing? Nope, you're still good. Okay, cool. So I need to figure out where that's at. Proc, okay, all sims, sudo, grep. Ah, too many devices. AVM device ioctl. That's definitely not where I want to go. See, I think the thing is called debug. All right, if any of you watching know offhand how to get cool. Okay, that is all. Damn. Oh. Okay. Oh, but even if I'm sudo, I can't see it. That's interesting. Okay. Okay. Okay, I definitely can be root. Cool. All right, you're gonna see me Google around a bit. Get address. Am I not running it in the VM? Ha! Thank you. Thank you. Thank you. I assume this is a problem that happens all the time then. Should probably change this so it like changes color or something when you're in the different VM. Proc KL sims. Yeah, there we go. Great. All right, got there. Cannot debug from within a VM. That makes actually a whole lot of sense. Cool. Break star. All right, done this, done this. Now let's execute that POC from within the VM. Yay. All right, sweet. This is really cool. Okay, so we stopped because we're at the start of this function. We are going to have our indirect call here, so it's only two more. Of note, this is what we're going to take a look at of this call stack. So we have this call stack where we ended up here at this proc reg unlocked ioctl, which then called our thing, but that came from VFS ioctl, file ioctl, do VFS ioctl, whatever, all these ioctls all the way back. Cool. Okay, so single step one instruction. I should be at the compare. So checking it out here. Compare ESI to that, and then jump there. So let's check where we are. So now jump not equal. So now at 18. Yeah, so now we're at that call. So now we're gonna call, that's gonna call into something else. So we're just debugging this. So let's step through to see what happens. Okay, we're in this, and then step. Okay, and then another step. Step. I guess I should just continue so I can see where it fails, but. And rip. All right, cool. We've achieved control flow. So we've hijacked the control flow. We've set it here, 41, 41, 41, 41, 41. 10i. So we can do something like we can make it fail, or we can make it succeed by jumping back here. So to call in there, bypass this ret 0, this is the ret 0, and this is the ret -1. So we could actually, if we change that to here, if we change that actually to here, oh lordy. All right. Could continue. Okay, go away, VNC. Now, if we compile this POC and run it again, of course I made that whole speech about dash out. Okay. Okay, and we can look, and our argument here should be 20, yeah. So if we run this and continue and go back, it did output 0? Why in the world did it output 0? Oh, because it called into that function which returned, and then that returned. Okay, great. Let's, lols. Right, we actually, so we jumped that function call. So if we look at here, right, this decompilation, we called the function. That function itself returned -1, but then when it came back, it just returned 0. So, all right, we got it to run and it did stuff. That's good. Okay, so the idea is this is where we are. Let's go back one more time because I want to go here. POC me baby one more time. Okay, POC. Great, got here. So if we look at, let's go step 2 more, step. So this is the situation where retspill is supposed to come in, where we get to this point where we have control flow hijacking. And now we want to understand, but again, so typically you have control of the heap. Like here we have directly on the stack, looking at this function, we have absolutely no data on the stack, right? We just have data that are passed in these arguments, which should be passed through registers. And so that's, and even those are optimized out. So if I, yeah, what was it? What did I pass in here? 20. Yeah, so 20, yeah, we can see here. So I'm controlling, I have R13 and R14 that I technically control. But actually one of the key questions that I don't know yet is how much of these arguments can actually come from me, the user, when I pass these things in. So that's actually something we'll look at. So here's the challenge, right? We want to start ropping. We want to be able to rop, pivot the stack, do all that kind of cool stuff, call arbitrary functions. Right now we can call functions, but we get like one function call and then we're done. And we can't jump back into our own shellcode that's in any of our user space programs. So essentially you have this problem of, all right, I have data, how do I actually achieve my goal? So let's look here. Yeah, okay, cool. And this happens all the time. So this is like, and again, the interesting thing is the triggering of calling this function. So let's say we've overwritten this, done the control flow hijacking, we've overwritten it. Now we just need to trigger this over and over again. So now we can trigger this. So the key idea that we have in this paper is that, and where the spill part of ret spill comes from, is we're thinking through us as attackers when we're calling a system call. What data do we actually control? And that comes back to this nice person here Oh, I wonder if I do this, I will get hit every time, but that's okay. Ah, okay, I don't think you're really helping, so you're going away. Okay, we're gonna set a breakpoint right on do syscall 64, which will of course hit many, many, many times. So uh, this may have been a bad idea. Okay. Now the question is, can we just look this up? Ah, do syscall. There we go. Okay, so first adds this random offset. Actually, it may have been to our stuff, but anyways. Syscall enter from user mode. Let's go there. Enter from user mode work. Bah, I want to trace enter. Okay, don't need to do that. So essentially, fundamentally, ooh, okay, cool. Maybe this is where we're going. No, do syscall sys64. I think this should be the one. Oh, wait, is it whoever calls this? Because the PT regs. All right. Anyways, enter from user mode. Enter from user mode. All right, it must be in the paper. Yeah, okay. So, okay, it must happen before we're doing this. But essentially, right, if you remember the separation of user space and kernel space, so you are transitioning from user space to kernel space because we made the syscall. At that moment, the CPU just switches to kernel mode. So it switches to kernel mode, it starts this syscall handler. But every data that's in that register all comes from you, the user space process. And that's what we were just looking at. This ptregs data structure has a structure that has all of your registers. So 65. Oh, sick. Okay. Wow. Linus is getting a ton of. Look at all them citations. Okay. What did we say it was? 65? No. PT rigs. Yeah. 65. Okay, it is PT regs. Cool. Yeah, cool. All right, so PT regs. So this is the data structure that has all of our registers. So this should, yeah. There's if defs, right? So this is 32-bit. This is, yeah, so these are all the registers for 64-bit, are 15, 14, 13, 12, the base pointer, BX, 11, 10, 9, 8, A, C, D, S, I, D, I. Oh, syscall number, interesting. So this is a data structure that exists that gets put onto the, like, so your instructions are specifically copied. Sorry, not the instructions. The value that's inside these register values, because again, remember, so we're transitioning from user to kernel space. We need to save the context of the register, what values were in there in user space. So that way when we return from the system call, we can go back where we're supposed to go. And so that's what we're doing in here. So this is what we get And maybe I needed to debug before it. Wait, why am I all in here? Oh, because I don't remember that I'm in this thing. Yeah, so maybe we need to stop here. Again, system calls are happening all the time. So FC, entry 64, sick. Okay, plus 84. Wait, did I say P trace? No. Beautiful. Just magical. Yeah, sweet. Okay, so this will be, okay, assembly code. Where are we? In the debugger one, roughly 184. Who knows if it's the right version, but let's say around there, 184-ish. Switch to assembly, something like this. Call save registers, push RBP, push. So this gets pushed onto the stack, and then great. Sick. Okay. 64-bit system call instruction entry, up to 6 arguments and registers. Is the only entry point used for 64-bit system calls. Cool. Registers on entry. RAX is the system call number. RCX is the saved return address. R11, ooh, saved R files, interesting. Then we have RDI, RSI, RDX, R10, R8, R9, only called from user space. When user can change pgregs foo, always force IRET. I don't know what that means. That is because it deals with unconnectable addresses better. So this says that this entry syscall 64 is actually what gets created. And can we break there? Assembly code, but we should be able to do it. Oh, there we go. Yep, entry syscall 64. Okay, get rid of this. Yep, okay. Here we are, entry syscall 64. Yeah, okay, bang, bang. Cool. So yeah, we are swap this some instruction. I vaguely recall what this does. Swap the GS base register, so swapping things. Because if we look up here at the registers, I don't know where we came from. Oh, actually, we can look. This is like a pointer into user space that's where we actually came from. If this is correct, that RCX is the return address, RAX has a syscall number, so we could look at the syscall number that says that this is E, and that's there. And so basically all of our data is then going to be stored onto the stack. So with this, first we're going to swap these things, then move this per CPU var into RSP. So this is going to then set up the stack for our task. So this is then, I guess our stack pointer must be the user space stack pointer. Yes, this is RSP. This looks like user space stack. But we do this, and so we should then, after we step, come on, baby, step, we'll see that the stack pointer updates. And at this point, I believe we've been in user mode. Is this what the switch to kernel CR3 is? I'm not 100% certain what that does, but that's okay. Okay, so now the stack pointer points to that the same value? It didn't change. Okay. Oh gosh, no, sorry. That's of course I'm getting thrown off by AT&T syntax versus Intel syntax. This is move RSP into the per variable, per CPU var. Then let's see what's next. What's next? Exchange AX with AX. Move CR3. Move CR3 onto the stack pointer. BTS branch, probably something off the stack pointer. Okay, and so align the stack pointer. Oh yeah, move RSP back into the CR3. So it's using the stack pointer as like scratch basically, and then setting up this CR3 register. Okay, then moving this GS into RSP. This must be, yeah, I see. This is a macro, this per CPU var. So that is then setting up RSP. So now the stack pointer should point to, yeah, so this is now kernel, and we can see because the higher bits are set that this is definitely kernel stack pointer. So now we're on the stack pointer for this thing. Now we're going to construct, yes, okay, so this is exactly where this happens. So constructing stack ptreg on stack. Oh yeah, this is where we are here. So this is where we are pushing these values, so like pushing R3, pushing RCX, RAX, right? That's ptregs IP. This is creating this on the stack, and then it's going to eventually do syscall 64 right here after it sets all this up. So all of, not all of, but a lot of our data that comes from us from user space is actually stored by this interrupt handler on the stack before it processes the system call. Why do we do this whole digression here? Well, because now we essentially do control data on the stack. So the previous statement that we said that like, hey, we don't control data on the stack, that's not true. We actually do control data on the stack. We just need to be able to get to them. Cool, okay. So, and let's see this in action. I need to take away all these breakpoints because it's way too much. Disable 2, D3, D4. Okay, that was cool though. Okay, so we kill that here. We have our POC. So our POC now calls that to redirect control flow. So now comes the question of how do we get this to do what we actually want it to do? How do we control those values? So we're going to use some, actually we can see here, SSSP flag CSIP. Okay, yeah, let's do, no, that'll mess it up. Okay. I want to, all right, I gotta look at, Kyle has a POC that I'm gonna steal from 100% because I hate this syntax here. And let's call this int trigger ioctl, or trigger control flow hijacking primitive. Void star, let's say arg, whatever, wherever we want to go to. So it's just going to be this, right? We have this, boop, boop. But what I'm going to do is I'm actually not going to call ioctl here like I desperately want because this is so easy. What I'm going to do is do this all in assembly so that I can control the things that get set. And that way we can see that these values, how these values translate. Okay, this syntax, the assembly here is a little weird, so I'm just going to use what we actually want to do. Okay. So 15, 14, 13, 12. So you can see different patterns in here, right? 15 is 41, 14 is 42, 43, 44, 45, 46, 47, 48, 40, and we will leave those now. I think this is just for an example. Yeah, we'll leave those for now. We will need to, so now we're going to need to go all the way to a syscall. Okay, so the system call is going to be here, and oh god, I need to remember to turn off assembly mode, otherwise that will like really mess with everything. If you don't do that, you are going to have a bad time. Okay, so assembly mode. I don't want to push RBP, whatever. Let's look here. Okay, now our fancy dancy x86-64 syscall table. Go to our friend Mr. Chapman. Cool. Ah, shoot, we do have these freaking arguments. Int f. Let's just do. That'll be up here. You know, just use globals if you. This is the part where you can cheat things and not engineer things correctly by just yeeting something into the global variable. Okay, so I'm going to call this ioctl. So that means this RDI will need to be move RDI FD. I think that'll just work, which is absolutely bonkers, but I think that will work. And then hey, buddy. Okay, it's also number 16, so RAX needs 16. And ioctl FD, the command, that's going to be RSI. 1337. And then finally move into RSI RDX, ARG. And syscall, and then I'm done. Oh, maybe the ret. I need to freaking extract that. I think you need to do something like move into. This one is in here. I absolutely hate this. Yeah, okay. Into, let's see, %1 RAX. And okay, and then there's this absolutely just stupid syntax. R ret. And then this, no, I don't need to, I think the equal means you write to it if I was a betting man, which let's say I am. So arg is going to be %0. I think that's how that syntax goes, but oof, what a terrible, terrible syntax. Yes, it is, Mitch. Yeah, we're doing retspill. We're trying to get close to retspill. See if that baby compiles. Expecting a void star, but the argument has a type. Okay, I don't care about you. Expected but before equals. Well, darn. Oh, lols. Okay, what a great syntax. Hey. Okay, output operand lacks equals. Input operand contains equals. Output operand, man, I think this is one of those times you should just be able to use ChatGPT. Okay. input operand, output operand. Oh, I think we're close. Unsupported instruction move. Yeah, how could you move? Okay, I don't think we want to do this. Let's just try this. Okay. 15, 14, 13, 10. Cool. All right, debugging by. Oops, that would be why. Okay, that works. So let's see where you fail. Show me you fail. All right, I guess you are in here. Let's see, is my intuition correct? Nope. Oh, FD cannot be used. Oh. Okay, we're almost there. Let's see, FD is the one that's wrong. Yeah, okay, well, let's just put that here. And that will not work. Uh-oh, then no PIE. No pi. All right. Wait, shoot. I don't want to do that. Okay, we're almost there. Okay, who cares about return values anyways? Okay, so we did all of this to check. So we are at, our stack is here, here. Let's start looking. Okay, but that's back, wait. Giants, okay. Okay. There we go, found them. Sweet. So starting roughly, let's say here. Yes, okay. So I get my, oh, there's a way to search, right? So I guess I didn't need to go that far. Okay. What was our RSP? 60. Oh, wait, 13E. Yeah, yeah, okay. Duh. So this, what this shows is that our data is actually on the stack uh, from our user space program. So let's take that again. And we have, there we go, our 41s, our 42s, our 43s, our 44s, our 46s are down here, but our 45s are up here. Our 40s are down here. We have 46, 48, 47. Um, cool. So using all of this, we were able, I bet this 3 is actually our RDI, but again, RDI, RAX, RSI, RDX are all things that we can't change because these things like RDI, uh, all this stuff is something that will get passed to the function eventually. Cool. So what this means is now we can control values on the stack from where we are. Um, and so with this in place, now we can start to, for instance, set our control flow hijacking. So let's, oops, that's not where I wanted to step. Let's step over here. Boom. Yeah, so at, what is it, roughly 110 hex, x20 giant x dash RSP plus 0x110. No, yeah, 110. Too much. Oh, 90. Wait, that's not right. Fucking hex math is insane. 1A. Yeah, so we can get, cool. Okay, yeah, so we can get there at like RSP plus F0. So because there should be a fixed offset from where we are here, we can then use a gadget in the kernel that redirecting to the gadget that allows a stack pivot and does a, so like where was the one? There's an example in the paper. All right, and then we already looked at PT regs. Ah, yes. So something like stack shifting gadgets, for instance, would be one of the things that we can do, like adding to RSP that gets us into here. Now, we only looked at one possible place that data is stored on the stack. So this, in this red spill example, we looked at the, let me find in the paper, the the preserved registers, so the PT regs payload. But there's also other things. So depending on the system call, there could be the calling convention. So anytime data is stored on the stack, let's actually search through. I can't remember the GDB command for this. I know Jeff. Oh, great. Oh, I wonder if I could get it to go backwards, but that's okay. Plus. Yeah. We could see if there's more. Anyways, that did not work, but that's okay. So as the calling convention, so register values can spill onto the stack from user space through callee saved or caller saved registers. So we know that through the calling convention. Another way is uninitialized memory. This is actually very cool. And the other one is like data copied to the kernel stack. So for instance, like in this code here, you have this stack PP is, I don't even know what this is, but the important thing is that it's copied from user. So it comes from user space onto the stack. So it's a very clear case where you'd have control on the stack. And then you should look at this weaponizing this. Even though you only have, let's say, like 5 to 7 gadgets that are here in this payload, this actually can be used to do. You can call it several times. So the very cool thing is you can call it in a separate thread, and that thread can do things like read write, and it doesn't need to clean up because it can just die, and that thread dies, but the side effect still remains, which is very cool. And this way you can get arbitrary read writes or executes through this, which is very cool. I'll finally plug, I haven't tested this, but we have a repo here and a tool. This tool allegedly should be able to do this automatically. Whether it can is a different story and can generate these payloads automatically. But what I find helpful is in here there's the demo, and there's a POC for this specific vulnerability that uses this technique that has a lot of cool things in here. You can see the there is, actually triggering the bug, but that's not the interesting thing. The interesting thing is here, like getting this payload to read a value from memory. And so you can kind of see this payload. This is what I kind of started with here, but you can see this payload and being able to do that here. But all right, I think my time is way up. So hopefully this helps illuminate a little bit this red spill stuff, which is pretty fun. All right, see y'all next week.